this, we're going to enter this in. So TA 70 plus 98.6 minus 70 equals e to the negative kt. So we're going to simplify this. It'll be 70 plus 28.6, because 98.6 minus 70 is 28.6, to the e to the negative kt. So now we can use the time at 6 p.m., the temperature at 6 p.m., which is 80 degrees. So that's the temperature of the time. So temperature is 80 at 6 p.m. equals 70 plus 28.6 e to the negative kt. Simplify this, we can go ahead and subtract 70 from both sides. That's going to be 10 equals 28.6 e to the negative kt. That's at 6 p.m. So at 7 p.m. we have a different temperature. Well, we don't really know it's p.m., do we? So at 7, it's the temperature of the body is 75 degrees equals 70 plus 28.6 e to negative kt. So again, we're just going to subtract 70 from both sides. That's going to give us 5 equals 28.6 e to the negative kt. So now to find, it's actually going to be t plus 1, because 7 is 1 hour before, 1 hour after 6. So now we can go ahead and cancel out like terms. So we're going to do 10, so temperature at 6, divided by the temperature at 7. So you can go ahead and cancel out 28.6. That's going to give us 2 equals e negative kt to t plus 1. So we can go ahead and cancel those t's out. So that's going to be 2 equals e to the k. And we're going to take the natural log of both sides to cancel out the e. So it's going to be k equals ln 2, which is going to equal the k, which is 0.693. That's the decay coefficient. Equals 70 plus 28.6 e. And now we're going to go ahead and equal what we found for k, which is going to be negative 0.693 times t. So we're going to do the same thing. We're going to subtract 70 from both sides. It's going to give us 10 equals 28.6 e to the negative 0.693 times t. So then we can go ahead and get t by itself, we can go ahead and divide 28.6 from both sides. That's going to give us 10 divided by 28.6 equals e to the negative 0.93 times t. So to get rid of that t, we're going to go ahead and multiply these by both sides by the natural log. That's going to give us negative 0.693 t equals ln 10 over 28.6. So now we can get t by itself by dividing both sides by negative 0.693. That's going to give us t equals ln 10 times 10 over 28.6 over negative 0.693. That's going to give us t equals 1.5 hours. So this means, since it's in unit hours, that means it happened an hour before, and it's also 30 minutes before as well. So that's the time elapsed from from when he died at 98.6 degrees to when he was found at 80 degrees at 6. So now that we have that, we can go ahead and find his time of death. And that's just going to be done by subtracting 6 minus 1.5. That's going to give us 4.5. And since these are both in unit of hours, it's going to be a unit of hours. This is 4 hours, so it happened at hour 4. And then we know that 0.5, half of an hour, is going to be 30 minutes. So since this is in unit of hours, that's going to be 30 minutes. So time of death was at 4:30. Is at 4:30. And this means that, so basically, we can interpret all these results using the fact that Newton's law of cooling is exponential. So basically, if we were to draw this out real quick, so an exponential graph would technically look like this. So it's going to go down like that, exponentially. So basically, if we started, we're going to have time down here on the x-axis and temp, temperature. So at 4:30, his temperature is a lot higher than when it was at 6, especially at 7. Kind of see. So at 4:30, it decreased a whole lot more than when it did going from 6 to 7, because per the 30 minutes from the time death to time discovery is actually 6.2 degrees per 30 minutes. And then from 6 to 7, and that's from 4:30 to 6. Then from 6 to 7, it is actually 2.5 per degrees per 30 minutes. So this just shows you that since it's an exponential decay, from the beginning it's going to decay, the temperature is going to decrease a lot more than it is at the end.